Today we're going to talk about one of the most critical topics in machinery health and vibration analysis: resonance. Whether you're an experienced engineer or just getting started, understanding resonance can be a game changer when it comes to identifying defects in equipment and keeping everything running smoothly. So what exactly is resonance? Well, every component in a machine has something called a natural frequency. Think of it like a tuning fork. When you strike it, it vibrates at a very specific pitch. Now, when the frequency of a machine's vibration matches the natural frequency of a component, something special happens. The vibration becomes amplified, sometimes massively. That's resonance. Here's a trick for you. When you're looking at vibration data, resonance often shows up as sharp spikes in vibration amplitude at very specific frequencies, typically when the machine is running at certain speeds. And if you see these, that's your first red flag. Why should you care? Well, resonance can cause major damage. It's like pushing someone on a swing. If you push at the right time, they go higher and higher. In machines, this amplified vibration can crack components, loosen bolts, damage bearings, and even lead to full breakdown. So you'll want to catch it early. For example, have you ever seen pipes shake when a machine hits a certain speed? This is likely due to resonance. Pipes, just like other structures, have natural frequencies. When the machine's operating frequency matches the natural frequency of the pipe, it can cause it to shake or vibrate significantly. This is why you might notice pipes rattling or shaking only at certain speeds. It's a direct sign that resonance is happening. So, how do we identify resonance? First, we use vibration analysis. Look for significant peaks in the vibration spectrum at a specific frequency. This is a strong sign of resonance. If you see peaks that repeat at multiples of that frequency, what we call harmonics, you've got a pretty clear picture. If you want to get really specific, you can run a test called modal testing. This helps you figure out the natural frequencies of individual components, so you know exactly which ones might be resonating with the machine's operating frequencies. All right, now here's something important. Resonance is often speed dependent. You'll typically see it when a machine passes through a critical speed or range. So if you notice the machine vibrating excessively at a certain speed but not at others, you could be dealing with resonance. Let's break it down with a practical example. Imagine you've got a motor running at 1,800 RPM. You notice a significant vibration spike around 30 Hz in your vibration data. Now, if you find out that the natural frequency of a nearby pipe support is also 30 Hz, guess what? You've likely hit resonance. That pipe support is vibrating in sync with the motor, and if you don't address it, it's only a matter of time before damage sets in. Here's another trick. If you suspect resonance, try a simple speed sweep test. Slowly ramp up or down the machine's operating speed and observe the vibration. If you notice vibration amplitude increasing at certain speeds and dropping off at others, that's a clear indicator you've found resonance. So what can you do about it? If you've identified resonance, you've got a few options to fix it. First, you can change the stiffness of the component. Adding supports or bracing can shift the natural frequency away from the operating range. You can also add damping materials to absorb some of the excess energy. And if possible, you can adjust the machine's operating speed to avoid those critical resonant frequencies altogether. To sum it all up, look for high vibration peaks at certain frequencies, especially if those peaks repeat in harmonics. Keep an eye out for speed-dependent vibration patterns, and if you find resonance, take action to adjust stiffness, add damping, or change the operating speed. Identifying resonance can save you from some major headaches, not to mention costly breakdowns. If you're serious about improving your maintenance strategies or troubleshooting machinery, understanding resonance should be one of the first things on your list. It's a small change in how you approach vibration analysis, but it makes a huge difference in preventing long-term damage. Now, here's a real-life example that some of you might relate to. I used to have a car that whenever it went over 60 miles per hour, the steering wheel would start shaking. At first glance, it might seem like an alignment issue, but what's actually happening is a classic case of resonance. Just like in industrial systems, the car's tires or suspension can vibrate at a certain frequency, and when the car hits a certain speed, that vibration can match the natural frequency of the steering or suspension system. This causes the shaking to be amplified at that specific speed, just like with resonance in machines. Here's a trick. If your car shakes only at specific speeds, like-minded, it's likely a resonant frequency issue. This can often be fixed by rebalancing the tires or aligning the wheels, which shifts the natural frequency and reduces the shaking. To summarize, resonance is a critical concept in machinery health. It occurs when the frequency of a machine's vibration matches the natural frequency of a component, leading to amplified vibrations. Identifying resonance involves looking for sharp spikes in vibration data, especially at specific speeds. Addressing resonance can involve changing component stiffness, adding damping materials, or adjusting operating speeds. Understanding and managing resonance can prevent significant damage and costly breakdowns. If you found this video helpful, please subscribe to our channel and like this video. Your support helps us create more content like this.